Hello, my name is Lily Alterman, and today I'll be presenting to you Lab 6, Magnet Molasses. Now, the purpose of this lab was to collect the data of a magnet falling through an aluminum foil tube. I then was supposed to use this data to observe and apply Faraday's law, and then I also created a computational model showing Faraday's law in this circumstance. Now, the results of the lab is a little preview. The computational time I calculated was 3.877 seconds, and the experimental time, which was an average of 5 trials, ended up being 1.378 seconds. Now, as a little introduction, Biot-Savitz's law describes the magnetic field generated by a constant electric current. Now, this is very important for this lab and is resembled by this equation here. It is the change in B, which equals our magnetic constant, our current, times the cross product of the length segment in the unit direction all over the distance squared. Now, the magnetic field of a dipole is a model of an object that generates a magnetic field distinguished by two opposing poles, meaning a north and a south pole, which is what we are saying our magnet is in this circumstance. And it can be seen by this equation right here. An important part here is this mu is the magnetic dipole moment. Now, Faraday's law is a change in magnetic flux generating an EMF. The EMF exists because of the change in magnetic flux, creating a non-Coulomb electric field that curls around the perimeter of the area through which the magnetic flux is flowing, and is represented by this equation right down here. The induced voltage is equal to the opposite of the number of turns times the derivative of the magnetic flux over time. There's a few more concepts to start the lab. We're also applying Newton's second and third laws here. Newton's second law, also known as the momentum principle, relates the total interactions to the changes of the motion in the system, and is represented by F net is the change in momentum, which is P over the change in time. And then Newton's third law, you've probably heard it before. For every action, there's an equal and opposite reaction. For example, F1 is our action force, F2 is our reaction force, and it is the opposite of F1. And Ohm's law, which we'll get into a little bit later, it's just a relationship between voltage, resistance, and current, and it's V equals IR, and it can kind of be seen through this little image right here. Now, as a little introduction, the programs I used for this experiment were WebPython. Also, to get my timing data for the experimental portion of the lab, I filmed and took the time from the video using an iPhone 13 and 360 ping. So now the initial conditions. Now I assumed in this that the only two forces in the system acting on the magnet were the gravitational and magnetic forces. I also assumed the bar magnets acted as a magnetic dipole, and I assumed that the air resistance was negligible. And as you can see, this is a little force diagram representing the two forces acting on my magnet in this system. The system also consisted of the bar magnet, the tube the magnet fell through, which was made of cardboard and aluminum foil, the top of the table, which also acted as the ground the magnet fell to in this experiment, the surroundings for everything else around the lab, like the people and the computers and such on the desk. The magnetic properties, the mass was 0.025 kilograms. The magnetic dipole moment was found to be 5.1135 A times meter squared, which was found in the previous lab using this equation of math right here. The two dimensions were also the length being 0.46 meters, the width being 0.005 meters, and the inner radius being 0.02 meters. Now, the procedure for my experiment was we got the system set up as seen to the right in this little video right here, and filmed the drops of the magnet going through the tube and the time it took to hit the ground in the system. Through that, I got this data right here and ended up getting an average change in time to be 1.378 seconds. Now that I took the data previously found in this lab to my WebPython simulation, right here just takes the properties of the tube and numerical parameters into the simulation, along with the properties of the magnet. This part of the code right here is just visualizing the bar magnet, and then this part right here was creating the tube of aluminum foil as the series of rings stacked along the y-axis, so I can use that to further calculate later in the simulation. Then in my code, I continued to define the initial conditions as this right here, time was 0 and velocity started as 0. And then I used this equation right here. This was for calculating my magnetic field with bar magnet using this formula right here. And then this formula right here was used for calculating the magnetic flux as stated in this formula right here. And then here's just the simulation loop I put it through so it would model and simulate the bar magnet actually falling through the tube. I further continued the code by calculating the magnetic force from the tube of the magnet and then calculating the typical B field at each ring. And in this simulation code, the magnetic field is assumed to be axis symmetric. Then right here, I just found and wrote out the force of the magnet and the force of gravity, used it together to find the F net, which was then able to use Newton's second law to have the magnet position and velocity update. Then I just used this function right here to plot the graph of the velocity versus time for the magnet as it dropped, which resulted in that image right there. Finally, I found my final results for the WebPython simulation to be the time in tube spent in seconds being 3.877, and it can be seen being modeled in the video right to the right. And on this graph, I found that the force of gravity was greater than the force of magnitude in this section right here. When it is basically a straight line, the force of gravity equaled the force of the magnet, and then right here, once again, the force of gravity was greater than the force of the magnet. And then just to sum up, my computational time was once again 3.877 seconds, while my experimental time was 1.378 seconds, which did differ vastly. Some of the possible errors for this could have been that the magnet hit the side of the tube, or other forces acted on the magnet, impacting its fall speed. There also could have been human errors in the measurement, i.e. the timing was off and not as precise as it could have been, or just it was slightly off in my exact timing of when I said the magnet dropped. And then the air resistance exists in real life, which I did not take any account for in the simulation. And also the magnetic dipole moment calculated last lab could have not been the exact magnetic dipole moment for this lab, as we think we use the same magnet and all the magnets should be pretty similar, but there could have been some inconsistencies that we did not account for. Also, I did get vastly different values for my experiment and my computational data for the magnetic dipole moment last lab, so that could also impact this lab too. Now for the first what if question, decreasing the resistance would increase the induced current as the voltage stays the same and Ohm's law states V equals IR, thus this would produce a stronger opposing magnetic field and slow the magnet more. And for the second what if, since the model was calculated using rings, if there was holes or slots cut into the tube, there would be less of these current rings within the tube, thus producing a weaker opposing magnetic field, causing the magnet to fall faster. Thank you so much for listening and have a lovely day.